Hi, and welcome back to Unit 3 of API Can Code, Data Science Practices. Today in Lesson 3.2, students are going to build on what they learned about data visualization from the last class with actually doing some of these techniques and creating some of these graphs in CodeApp. We start with a warm-up that shows nutritionists versus general Americans' perceptions of health of different foods. We ask a few questions to parse out students' understanding of features on the graph. We recap lesson 3.1, which talked about data visualization, especially making sure that depictions of data are honest and clear and not misleading or unhelpful. We're going to spend most of today and the third unit focused on CodeApp. CodeApp is a click and drag data analysis platform offered by the Concur Consortium and is available through the web app. The easiest way to get into CodeApp is to go straight to this link, codeapp.concur.org/app. From here, students are able to do two things, either create a new document or open an existing document. The Open Existing Document button will be very helpful for when we're working through our practice examples early in the unit, and the Create New Document button will be very helpful towards the end of the unit and into the final project as students start to do their own analyses. Once in CodeApp, students will see the following toolbar. We'll discuss many of these components specifically at different points in the third unit, but some of the most important are tables, graph, and map, which are used to create a table with data in it, create a graph to visualize that table of data, and the map button. Students will also often use the menu button to do different things such as loading data or saving data in different ways. We also want to go over a few options on the Graph Inspector panel, which will pop up when a student clicks on a graph. Most of these students will not need to use too often in the course, but the big exception is the ruler button, which students will use very frequently. This ruler button will be used to calculate and show different statistics, including mean, median, and standard deviation, right on the graph. What we want to start students out with today is opening the mammals example in CodeApp, and they can use the link right in the slide, or they can open an existing document and find the mammals example. We want students to think about what form the data is in. They might notice that this is tabular form instead of the JSON format that we've been working in for most of the second unit. We also ask them what kinds of variables are stored in this dataset. Thinking about what stage of the DIKW model this analysis is in, we have both the data itself, the table on the top, and we also have information processed into these three data visualizations down below. We're going to go through a few of the charts that are pre-created and then have students create their own charts. So looking at this graph, we want students to identify that this is a dot plot, and it shows all the names of the different mammals. This is not a particularly useful graph for showing much of anything because it only has one variable, and that variable is a name. So of course each mammal has a different name. That makes sense. Our next visualization is a little more helpful. This is another dot plot, but now we have lifespan in years, which is a quantitative continuous variable on the y-axis instead of the nominal variable from the last slide. This graph shows the distribution of different lifespans across all the mammals in our sample. We're going to look next at this graph between diet and habitat. This is another dot plot, although we might call it a binned dot plot, and it also has a color code legend laid on top of that binning. This graph shows the diet of different mammals and their habitat in addition to that information. So you can see that the mammals that eat plants and both live on land exclusively, and the mammals that eat meat, some live in the water, some live inland, and some live on both water and land. There's actually only one of that last example. We'll display this GIF to show students how to make a graph in CodeApp. Students will start by clicking the graph button and then dragging two variables onto the X and Y axis. Students are also able to drag a third variable if they want to onto the points themselves to color them with another characteristic. We'd like students to practice this skill still using the mammals example. So we want students to create their own graph. They should use one or more variables, so that what might be one, that might be two. Enterprising students might figure out how to use three or more. But they should use this graph to show something that they're curious about from the table and then share that with the class. We're now going to walk students through creating some specific graphs that we can look at together. First, we'll look at the distribution of mammal heights. Students should be able to make this graph by dragging height onto the x-axis. They should think about what this tells you, what it means to be further to the left or to the right on this graph, which means you'd be shorter or taller, and also the question, where are most of the data points? You can see that they're mostly clustered around 1 meter, which suggests that most mammals, your average mammal, is probably around 3 or 4 feet in height. From our dot plot example, we're going to move on to a scatter plot. In this graph, we want two variables, mass on the x-axis and speed on the y-axis. We asked students a couple questions similar to the last slide about this graph. One notable thing about this graph is that while there is somewhat of a relationship between mass and speed, it's really hard to see because we have three very large mammals that are forcing the x-axis to be very compressed, I would say, especially towards the lower end of the scale, because these three mammals are so much larger than so many of the other mammals that they make it really hard to parse out how big the smaller mammals are. So students might notice that and refer to those as outliers that make the graph difficult to read and difficult to interpret. We talk a little bit about outliers here. An outlier is a data point in a graph or in a set of data that is very much bigger or smaller than the next nearest data point. We visualize this on a dot plot as being simply far to the left or to the right of the rest of the points. We visualize this in a scatter plot as an outlier that really does not fit the pattern of the rest of the points. So we want to take students back to this graph and look for outliers. Students will probably notice that the mammals with a mass of about 4,000, 5,000, and 6,500 kilograms are major outliers. We also want them to think about what the pattern would look like without these outlier points, and whether that would be similar or different to what they see with the outlier points. Identifying outliers on a scatter plot can be done by looking for points that are unusually low or high in the y direction for where the rest of the points tend to fall in the x direction. One thing that can be helpful is to draw a mock line of best fit through most of the data and see how far different points fall from that. A point that falls very far from that line may be an outlier. Some outliers might be present just because of recording errors or measurement error. Imagine a heart rate monitor reads 120 BPM and then a researcher writes down 1200 BPM. That's going to be a major outlier because most heart rates are nowhere near that. But other outliers might be present just because the real measurement is just unusual. Yao Ming, for example, is a walking outlier. He just is that tall. So next, we're going to have students create our final graph, which is diet related to habitat? This is going to be a two-way binned dot plot. Because both of the variables are categorical, this will create a binned plot instead of a scatter plot. So we want students to put habitat on the x-axis and diet on the y, and interpret the graph with the questions shown. Sometimes two variables are highly correlated, but not always causally linked. It's important for students to know this because we want to make the point that not all relationships actually mean something. We give the examples to the right. For example, solar power generated in Argentina correlates really strongly with Google searches for do vaccines work in any particular year. But these are probably more related to increased vaccine development and increased solar power just happening to happen at the same time rather than one causing the other. So we do want to make sure to emphasize this difference that correlations don't always mean there's a causal factor going on. Walking back to our mass versus speed relationship, we asked students, do you think there's a causal relationship here? Or is it just a random correlation that we're seeing spuriously? Finally, we're going to explore some map data. So we want students for this exercise to open the roller coasters dataset. Again, this is one of the built-in datasets, so students can do the Browse Examples button, but they can also just open it from the link in this slide. We want students to press the map button on the top left, which should automatically generate a plot that looks very much like this. We have a few questions to walk students through identifying particular pieces of the map. For example, looking at DC and seeing if there are any roller coasters there, clicking on the state of Maryland on the map and seeing what that selects in the table. Spoiler alert, it should select all the roller coasters that are in Maryland. We want students to create two graphs using any of the variables they find interesting. For one of those graphs, we want them to use at least two variables. In today's worksheet, they should be able to respond to the following questions. What variables did you use? What did you notice about the graph? And what do you think this tells you about the roller coasters? This is an opportunity, if you have time left for a brief class discussion, to talk about how those graphs got made and interpret them. Today's exit ticket asks students the question, which roller coaster would you most like to go on if you could? Students should support their answer by creating a graph. One thing, for example, if I were answering this question, I might create a graph of top speeds, and I might select a roller coaster that didn't actually have a super high top speed. So my graph would be helping me by showing me sort of the distribution of different speeds and helping me identify one of the coasters that was a lower speed coaster for this. And of course, this is supposed to make the point to students that we can use data science for various purposes, including something like selecting a roller coaster to ride. As always, thank you for tuning into these lesson videos, and thank you for teaching the API CAN code curriculum.